Okay, so I'm assuming the screen is being recorded and we are good to go. Okay, so today this is the second last section that we are going to discuss. It is one of the methods to solve differential equations. After this one, we'll be having very last section, which is 11.5. And since 11.6 is optional, we'll not be doing that thing, okay? But it depends, maybe we'll see what we can do the next week. And also we skipped 11.3, which is optional too. 11.3 is like one of the numerical methods to solve differential equations. Like we saw, we can do integration by some numerical methods, like we did trapezoidal rule and a couple of others. I think they did not fix this thing. Yeah, I'm sorry for that. But I think we don't need to worry. This is something inside the system and they will do it maybe at some point. Okay, so what is the key point here is you are given a differential equation and you solve differential equation by separating the variables. The key point is if you can rewrite your differential equation in this way, like any function of y times dy is equal to any function of x times dx. So this thing should contain any function of y, like any terms that only involve y, and right hand side contains the terms only involving x or any function of x. If you can do this thing for a differential equation, then we can solve that equation by using method of separation of variables. The question is, can we do this thing for any differential equation? And the answer is, what do you think? What should it be? Yes or no? No, obviously. Since there are notorious problems in differential equations which are very hard to solve, so separation of variables is one of the basic methods to deal with solving differential equations. But if you classify differential equations and you start with the order of the differential equation, separation of variables only helps to solve first order differential equations. Maybe we discuss in 11.1 that what is the order of a differential equation, and the order is the highest derivative that is present in that equation. So we are only dealing with differential equations of first order. What about differential equations of second order? You will be doing this thing if you are taking a course on differential equations. Differential equations of third order, you will be doing the same thing over there. And the differential equations of any order higher than 3, for example, maybe you won't be doing in differential equations course. Okay, because those are again like those are some of the equations which are not too practical, or maybe there are less practical, they have only one or two applications. Okay, and once we have a differential equation of first order, we can think of, can we separate the variables? If you can separate the variables, you can apply this method. If not, then you cannot. In summary, differential equation is given. and you check its order. So let me write order of differential equation. If the order is equal to 1, then you apply separation of variables. If the order of differential equation is not 1 or maybe greater than 1, it can be like second order, third order, or something else, then you don't need to apply this. Then you have other methods, for example. The order of the differential equation is 1. Then you check. The next question is, can you separate variables? Separate variables. This is the question, yes or no. So there are two options. If you can separate the variables, you apply 11.4, the method in 11.4, that is separation of variables. So this should be what we are doing. But obviously, every equation that we'll be dealing here will be a differential equation of first order. Then we have to only care about, can we separate the variables or we can't. So let's see. The very first example. The question is, using separation of variables, solve the differential equation. So this is seemingly very simple differential equation where you can multiply or divide something to separate the variables. For example, I'm going to write a step 1 of the solution, which is separate the variables. And how to do this thing? Like if you take this differential equation, negative x over y, and you multiply y on both sides, maybe you can see this y is cancelled and you are left with y dy over dx is equal to negative x. And now if you multiply dx on both sides, maybe let me put some space. You multiply dx here, you multiply dx here, and then you got y dy is equal to negative x dx. So we can separate the variables, hence we can apply this method of separation of variables. You can see this is some function of y times dy and some function of x times dx. Now the second step is, step 2 is integrate both sides. So as I was emphasizing for last a few weeks that we should know integration, so this is the point where we need to apply all the techniques of integration. Maybe integration for this problem is really simple, but you will see like this integration can be really hard at some point. It all depends on what's the problem, okay? So you take this y dy, you integrate, you take this negative x dx, you integrate. So what do you think? What is the integral of y with respect to y? The integral y dy. Calc 1. Or maybe y square over 2. Very good. So it's simply power rule. And what about right hand side? Negative is there, and integral of x dx should be x square over 2. Okay. So once you integrate, you know that you have to introduce a constant of integration. So we are integrating on left hand side as well as on the right hand side. Where should we introduce the constant of integration? Both sides? Both sides, but yeah, you're right. It should be both sides. But in practice, we only introduce the constant of integration on only one side, and that side is practically the right-hand side. You can introduce constant on both sides, but like there's no need to do this thing. So this is the constant of integration, and we are done. We're done with this problem. You separate the variables, you integrate, you're done. But you must introduce the constant of integration. The next point is, if you want, you can rewrite this in a very nice form if you want. If not, then it's okay. Like if you multiply 2 on both sides, this is y square is equal to negative x square plus c plus 2c. And you add x square on both sides, then you can write this thing x square plus y square is equal to 2c. And sometimes, since c is a constant and it can take any value depending on what is the initial condition, you can replace 2c by some other constant, k, for example, because it only depends on like what is the value of c and what is the value of k. And maybe we discussed this thing yesterday, that the solution to this corresponding differential equation is a family of circles. And you know very well that the equation for circles is x square plus y square is equal to radius squared. And radius is like you change the radius, you get a different circle. So that radius square is equal to k in this case. So you separate the variables, that's the first step. That's pretty easy step. But for some of the problems, you have to think about how to separate the variables. Second step is you integrate. And then in integration, you know very well that it is common to introduce a constant of integration. And that's it. Okay, what about this one? I want to separate the variables. So I'm going to start with multiplying dx on both sides. So dx times dx. So I'm left with dy is equal to, k times y dx. On right hand side, I can see there's a y, so I'm going to divide that y so that I can get rid of that y on the right hand side. So divided by y divided by y. So dy over y is equal to k times dx. Okay, so left hand side is a function of y, right hand side is a constant k times dx. So if you want, you can keep that constant on right hand side or you can take it on left hand side. It doesn't matter because that's a constant. Okay, so the next thing is we integrate. So what's the integral of dy over y? So this is natural log of y and this is right hand side kx plus c. Okay, so this is the solution of that differential equation, but as I mentioned earlier, we will write this thing in maybe in a different form. Sometimes this is called implicit solution. And the explicit solution should look like this. Y is equal to some function of x. So left hand side should only depend on y and right hand side can be like any function of x. So how should I write this thing as an explicit solution? What should I do? Like my question is, how can I get rid of natural log on left hand side? Yeah, exponential. That's very common. So left hand side becomes y and right hand side becomes e to the kx plus c. Again, I can rewrite this thing in this way. Can I do this thing? E to the kx plus c the same as e to the kx times e to the c. Because if you have same bases, you can add these exponents. Yeah.
Why wouldn't it be e to the kx plus b to the c?
No. Because once you have product, you can take the same base and you can add the exponents to get this thing. Yeah. So now what am I doing? Since this e to the c is a constant, I'm going to replace this thing with another constant because e to the c is like there are two constants. But since the value of c is arbitrary, I'm going to replace this thing by a. So the solution is a e to the kx. So for that differential equation, e to the kx multiplied by a is the solution. Now, since a is an arbitrary constant, you can choose any value of a. That will still be a solution. But k there is not an arbitrary constant because the value of k is coming from the differential equation. You can see in differential equation, k is there. But again, you can choose any value of k. Still, that would be a solution. But the thing would be that you put the value of k in the solution and you have to put the same value of k in the differential equation as well. Okay, so for example, if you choose the value of k to be 1, then the differential equation is dy by dx is equal to y. This differential equation says that, okay, give me a function y whose derivative is equal to the same function y. And we know that there is a single function whose derivative is equal to the same function. That function is e to the x. So the solution should be e to the x. And multiply by a constant a is like, if you take e to the x, the derivative is e to the x. But if you choose a different value of a, for example, 2, still the derivative is 2e to the x. So this is the solution. And also, you might be thinking, there is another function as well whose derivative is equal to the same function, and that function is 0. Because if you take a function 0, its derivative is 0. So this is also one of the solutions of that differential equation. And you can get this solution by choosing the value of a to be 0. If a is 0, then y is equal to 0. And y is equal to 0 is also the solution of this differential equation, but this is not an interesting solution. We call this trivial solution. So sometimes we don't need these solutions. Okay, so you know the method now. I will go to those problems which are like where you have to integrate by using some techniques, but these were like really basic. Okay, can you help me separate the variables here? They are saying that, okay, you can pick the value of constant k to be 1. So I'm going to do this thing. Or if you don't do it, it's all okay. So let's multiply dt on both sides to get this thing, negative k h minus 20 dt. And then we got this thing, negative k h minus 20 dt. So obviously, before solving any problem, we have to identify what are the variables. So in this particular problem, there are two variables. One is time, which is t. Another is h, which shows the temperature. So h should be on the left-hand side. So I'm going to divide by h minus 20. Obviously, I cannot divide by h only, since these are two things which are connected with each other. So I'm just dividing this quantity. So the left-hand side is dh over h minus 20, right-hand side is negative k dt. And then obviously I'm going to integrate. So maybe it is better to rewrite and then integrate. What is the integral of the left-hand side? Partial fractions, integration by parts, or simple maybe substitution.
Which one's, only?
Yeah. Yeah. Obviously, you have to do substitution. Yeah. So natural log of h minus 20. I should put absolute value, but I don't need to. And this is negative kt plus constant of integration. Okay, so this is the solution. And obviously, to rewrite this thing in some explicit form, we have to take exponential, which gives me h minus 20 is equal to e to the negative kt plus c and, plus c. I'm going to add 20 on both sides, 20 plus e to the negative kt times e to the c. But then I'm going to replace e to the c by some constant. So h is equal to 20 plus some constant, which is this guy, e to the negative kt. So this is the solution for that particular differential equation. This is corresponding to Newton's law of cooling or warming. We'll see in the next section where we will be dealing with some of the applications. What does it say that, for example, if you put t is equal to 0, this quantity would be e to the 0, which is 1. So we'll be left with h is equal to 20 plus a. And maybe we can find the value of a by using some initial condition. And the value of k is 1, so we can replace the value, the exact value of k there. So this will give us h is equal to 20 plus a e to the negative t. So maybe to understand this problem, we can look at this slope field as well as 3 different solution curves corresponding to different initial conditions. Okay, so if you want to understand this one, this solution, which is corresponding to this exact solution, which is h is equal to 20 minus 10 e to the negative t. What does it say that, okay, inside the room or inside some medium, the temperature is 20. This is the exact constant temperature you can see. And for example, if you think in Celsius, not Fahrenheit, then the room temperature is almost 20, 25, the normal room temperature, 20, 25 Celsius. Inside the room, if you put something whose temperature is 10 degrees Celsius, which is obviously lower than 20, this object is a bit colder, like you put a cold drink or something else here in a glass, and then you leave it for some time, the temperature of that particular drink will increase and eventually it will reach the normal temperature in the room. So if time is equal to 0, you put that drink out of like some refrigerator, for example. Initially the temperature is 10, then it keeps on increasing until it reaches the room temperature, which is 20. And then if you keep, for example, a hot coffee whose temperature is 30, which is not too hot, obviously, but then After some time, after 10 minutes, 15 minutes, the temperature would be close enough to the room temperature. As you can see, it starts from 30, it keeps on decreasing and eventually reaching the room temperature. And this particular problem is called Newton's law of cooling or warming. And this is modeled via this differential equation. We'll see in next section where we'll be solving like a problem with different situation, but the exact differential equation is this one. Okay, so this is the solution and this was a little interpretation. Let's talk about this thing, which is, we can think of this is an initial value problem where the differential equation is given to us, plus some conditions to find the value of the arbitrary constant. So, separating variables and then integrating. Here maybe separating variables would not be simple as compared to the previous problems. So dy by dt is equal to y square plus y square times t. This is the differential equation. What should I do to separate the variables?
Both sides.
Okay, let me do it. So that's the first step. So if I multiply dt, I have dy is equal to y square plus y square times t dt. Next. Yeah, very good. So we have to factor out y square. So sometimes this is the key point, like you have to factor out something to separate the variables. So if we do this thing, we'll get y square times 1 plus t dt. And what is the next step? Yeah, divide by y square. So left hand side is dy over y square 1 plus t dt. And we can see the variables are separated. And once we get this thing, we can integrate both sides. So obviously there are two main steps: separate the variables, and then the second step is integrate. I think integral of the right hand side is a bit simple as compared to integral of the left hand side. So obviously the left hand side is difficult. What do you think?
This has to be 1 plus t squared over 2. Oh, in parentheses.
If you integrate 1 with respect to t, is it 1?
Oh, no. I substituted here.
Substitution on right hand side?
Yeah.
Why? It's simply you integrate 1 and then you integrate t. Like you can separate. Integral of 1 is t, integral of t is t square over 2. Plus obviously a constant of integration. And what about left hand side? This is the most quiet class I got in my entire history. Obviously here at FSU I'm teaching third time, but before that I have taught at various places and it's like noise. noisy. What's that? Did I lie? No. Yeah, so left-hand side is really simple. Again, you apply this, what do you say? Power rule, because this is nothing but y to the negative 2 dy. You can write left-hand side in this way, and then you add 1 and divide it by whatever the new exponent is. So this is y to the negative 1 divided by negative 1, which is nothing but negative 1 over y. Because y to the negative 1, if you take it in the denominator, it becomes y. So negative 1 over y, negative 1 over y. So this is the solution. And I'm not going to write this in some explicit form, because I'm going to find the value of c by using this condition. This condition is like when the value of t is equal to 1, the value of y is equal to 2. So t is equal to 1 implies y is equal to 2. If you apply this condition in this star equation, then on left hand side it would be negative 1 over 2, which is the value of y I just substituted. Right hand side is 1 plus 1 half plus c. So you add, subtract, and do whatever you like. I think the value of c will be negative 1. No. No, 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 no. Negative 2. Yeah. Okay, and you just substitute this value back in the star. It will give you the particular solution, and this star is a general solution. T plus t squared t negative 2. So this is the particular solution. If you want, you can rewrite this in explicit form, and that's not difficult either, because you multiply negative 1 on both sides. That will give you, like, the right hand side will be 2 minus t squared divided by 2. I'm just rewriting everything. And then if you flip everything, the left hand side would be y and the right hand side would be 1 over everything, which is 1 over 2 minus t square over 2. So this is the explicit solution, but if you don't find this thing, I think this should be enough. This is the particular solution corresponding to the initial condition that is given to us, or this is the complete solution of this initial value problem. We should not call this initial value problem, because the value of t should be 0, because t is equal to 0 means you are starting at some point. So that's called initial value problem. But maybe you can assume you are starting something at t is equal to 1. Yeah, it's not an issue to make sense of the things in this way. Okay. So a time to do this problem. So I'm maybe giving you, what should I say? Maybe 10 minutes. Let me be generous here. So solve this initial value problem by separating the variables and find the particular solution. After this thing, I think there will be very last problem, and then we'll be done with this section. And then we'll be doing, like, maybe on Monday, we'll be doing very last section.